In this video, I'd like to show you how to solve two classes of problems. These two classes of problems are traditionally referred to as related rates and implicit differentiation. The game we're going to play with related rates problems is that there's a certain derivative that you want, but you're given a different derivative. Okay, so somehow you're going to have to relate the derivatives or relate the rates. Get it? And then with implicit differentiation, we're going to find the derivative of a function without necessarily solving for the function itself. So maybe there's some issues with solving for what the function expression is, or maybe we just don't want to solve for the function because it would take a lot of work. It turns out we can get the derivative without knowing or caring what the function is explicitly equal to given certain information. All right? So let's do some examples of both kinds of problems to make that more concrete. So imagine we had a garden, a rectangular garden, and let's say that the width of this garden was 3 meters and the length is changing. Okay, the reason the length is changing is people are moving the fence, parts of the fence around. So the length is increasing, but the width is staying fixed at 3 meters. All right, so you imagine whatever scenario you want for that to make sense to you, but the point is that the length is increasing. Okay, so here's a typical word problem you might see. Fencing for a rectangular garden is being adjusted such that the length is increasing at a rate of 4 meters per minute, while the width remains fixed at 3 meters. How fast is the area changing? So fencing for a rectangular garden is being adjusted such that the length is increasing at a rate of 4 meters per minute while the width remains fixed at 3 meters. How fast is the area changing? Okay, so can you see that I gave you one derivative, but we want a different one? I gave you L prime, you might call it, but I want A prime, where A represents the area. Okay, so the area of a rectangle is length times width. In this case, the width is 3, so the area is 3 times L. And both A and L are changing with time. Let me make that explicit by adding the time variable there so you can see. And the only way that the area function and 3 times the length function can be equal for all time is if their derivatives are equal for all time. That's important. All right, so let's take the derivative of both sides. A prime of t is equal to 3 times L prime of t. Okay, so we know what L prime is, it's 4. So now we know A prime. A prime is 12 meters squared per minute. 12 square meters per minute. Okay? So you see how first we found an equation relating the two variables we're working with, and then we found the derivative of both sides, and now we related the derivatives, and so we could solve for what we wanted. Okay? This is a related rate problem. Now, sometimes, but not always, you will use the chain rule when you do related rates. Let me show you another example that uses the chain rule. And then we'll move on to implicit differentiation. Okay, a balloon is being inflated such that the radius is growing at a rate of 1 meter per second. Excuse 2 meters per second. How fast is the volume increasing when the radius is 1 meter? Okay, so once again, I gave you one radius, but I want a different rate, I gave you one variable's derivative, but I want a different variable's derivative. The two variables we want to focus on are volume and radius. We'll call them V and R. Okay, so let's draw a picture of a balloon, and the R is whatever it is. The V is 4/3 pi r cubed. Hopefully you remember that from geometry for the volume of a sphere. And both V and R are functions of time. So let me make that explicit. Now you don't have to do this every time, but because this is likely your first time seeing related rates problems, I just want to make it as clear as possible. Okay, so now the only way that the two functions on either side of the equal sign could be equal for all time is if their derivatives are equal for all time. So let's go ahead and take the derivative of both sides. And for this example, I'll use our alternative derivative notation. So dv over dt is equal to 4/3 pi times 3r squared dr over dt. Notice I use the chain rule on the right side. Okay, and so now we related the derivatives, and so let's take it home now. So the 3's cancel. We have 4 pi r squared dr over dt. 4 pi times 1 squared times 2 equals 8 pi cubic meters per second. Okay? Now, just a reminder, this alternative derivative notation is nice when you've got several variables floating around so that you remind yourself what you're taking the derivative with respect to. Okay? Now let's move to implicit differentiation. Okay, so here's a problem that might come up somewhere in the world at some time in the future. What is the slope of the tangent line to any and every point on a unit circle centered at the origin? All right, I hope that's clear what I'm asking for. So we've got an XY plane, and we've got a unit circle. That's a fancy way of saying a circle with a radius of 1. Okay, and we want the slope of the tangent line at any point. So for example, if I was on this purple point right there, the tangent line would look something like the following. And so that would have some slope, and different points on the circle would have different slopes. All right, now you might say, well, hold on, this doesn't look so bad. I know what the formula for a circle is. The formula for a circle is x squared plus y squared equals r squared for a circle centered at the origin. In this case, the radius is 1. Okay, so far so good. But let me remind you that there's no function that has a graph that is a circle. A circle violates the vertical line test. So if you wanted to solve this problem, you would have to get two separate functions. You'd have a function for the top half of the circle and a function for the bottom half. Okay, and so you could do that, all right, but you can see already that there's some issues with dealing with the function, all right. Now, for more complicated problems, it might be difficult or even impossible to solve for y. Okay, but so for whatever reason, we might not care about what the y function is. In fact, this question didn't ask for what y as a function of x is. We just want the slope. Okay? Now, remember on related rates how we had a function equal to another function and we took the derivative of both sides? Okay, watch this. Let me move the y squared to the other side. Okay? Now, whether we're talking about the top or bottom, y will depend on x for either one of those functions. So I have x squared equals 1 minus y of x squared. Okay, so this last equation will be true whether I'm talking about the top or bottom. All right, for both, we have a statement that's true about both functions, regardless of whether we're on the top or bottom. That's all we need now, because the only way that those two expressions for x can be true, the ones on each side of the equal sign, is if their derivatives are also equal for all x. Okay, the only way that two expressions could be equal for all x is if their derivatives are also equal for all x. Okay, so let's then take the derivative of both sides. So 2x equals 0 minus 2y prime. Okay, and let's now solve for y prime. First, let me divide both sides by 2. So x equals minus y prime. So y prime equals minus x over y. See that? We solved for the derivative without knowing or caring what the expression equal to y is in terms of x. That's the power of what we call implicit differentiation. Okay? Let's do one last example. Now, suppose you knew that the relation between y and x was the following. Let me do it in black. Seems like a good way to start for some reason. Sine of y is equal to cosine of x. Let's say somehow in some physics theory or chemistry theory that somehow that showed up. Two variables were related by this equation. Okay? Now, you could get an expression for y by taking the arc sine of both sides, although arc sines are a little unnerving. Plus, you might not know what the derivative of arc sine is. Okay? I'm not particularly fond of arc sines, so let's use the implicit differentiation trick, which I was talking about. All right, so whatever y is, we know that it's a function of x. So to make, again, just to beat a dead horse, let me write y as a function of x. Okay, so both sides are functions of x. The only way that both sides could be equal for all values of x is if their derivatives are also equal for all values of x. So let's take the derivative of both sides, and be careful because the derivative of the right side with respect to x is easy, but the derivative of the left side with respect to x, not with respect to y, with respect to x, is going to involve the chain rule because we have a composition. Okay, so I'm going to write cosine of y times dy over dx. That's what the chain rule would give us. If we were taking the derivative with respect to y, yes, we wouldn't have that dy over dx there. Okay, now we can solve for dy over dx, and it's equal to minus the sine of x divided by the cosine of y. See that? Okay, so to recap, you'll often have a situation where you have a function equal to another function for all values of some variable, be it x or t or something else, And the only way that those two functions could be equal for all values of the independent variable is if their derivatives are also equal. And so we use that fact to solve for a derivative without necessarily solving for the corresponding function.